Okay, welcome back, everyone. Does everyone hear me?
Yes.
I can.
Yes.
Okay, good. First off, does anyone have any questions? Right. So before returning exactly to where we were last time, I want to discuss computation in lambda calculus and why it's relevant. And also, there's another reason why computation got motivated. I suppose I'll write down one of the rules that we had last time. We had this idea that if, for example, in some context gamma, we had some f and its type wasn't an arrow like we saw before. It wasn't just an implication, but it was a for all statement, which I'll remind you of later in the lecture, but implications generalize to for all statements. So suppose the type of f was this for all, let's say, x in t, some t. Some w. And suppose also that in the same context, we had some term a, and we were able to conclude that its type was t. Then what happens when you perform this evaluation this has type, does anyone remember?
T to W.
Well, we can think of f as having type t to w, but in a more general sense.
Oh, sorry, W. Sorry. Yeah.
Well, if we write w, the statement we can think of is, for example, later, we're going to have things like reflexivity. And then let's write something like x is going to be a term of some equality type, x equals x. So this is the equality type. This is an equality type. And that x equals x is introduced by this reflexivity rule. So we're going to have things like this. And then we can form logical statements of the following form. Consider the statements for all n, and we're going to have a notion of natural numbers that n equals n. Every natural number is equal to itself. So if we think of this, there's a type. That's an equality type. N equals n is a type, and terms of this type, again, we haven't discussed equality types yet, but this is going to happen soon, are proofs of equality. And so a term of this type is, well, give me a natural number, and I'm going to give you a proof that n equals n. That proof is reflexivity on n. So in other words, for any natural number, ID reflexivity n is a proof of n equals n. So in particular, ID reflexivity Z is a proof of Z equals Z, right? So in some sense, when we use a for all statement, we substitute. To prove for all, the proof is by the anonymous method. We leave n as an anonymous member of whatever we're quantifying over, for example, natural numbers. And then if we want to prove for a specific natural number, we substitute that into the proof, right? So in that case, if we look at this proof term, which is a lambda, and we evaluate this proof term on Z, we get Z equals Z, right? And you're saying that that would have type W, where W is the right-hand side of the implication. So that would be n equals n. So if what you said is true, then we would have that Z equals Z, reflexivity on Z was a proof of n equals n. But the problem is, what is n? Right? We see here, for example, that the right-hand side W is a proposition in which the variable being quantified over occurs in the statements. So when we apply, it doesn't make sense to say that it has type n equals n. N was only meaningful as a variable of quantification. So what do we do to fix this? I very, very quickly went over it last time, and I didn't explain it in full. But what did we sort of see? Or what do you see in this example?
Well, isn't n just some sort of meta variable?
Yes, but the meta variable is only meaningful as a variable of quantification. When we make an application, we've removed the for all, right?
Yeah.
Like W doesn't have a for all in front of it here in this line, right?
Yeah. It doesn't.
I mean, so for example, consider this term, right? This term right here. I told you to take it on authority. 1 second. That's this term right here is a term of the type that's written above it.
Yes.
But in which case, if we take this term and we apply it to Z, then if there's computation, if computation ensures the picture, then Z will get substituted for N inside of the body, and we'll just get the term ID reflexivity Z.
Yeah.
And this is a proof of Z equals Z, right?
Yeah, it is.
But it's not a proof of N equals N, because the statement N equals N on its own is meaningless. The statement for all N, for all nats N equals N is a logical statement, whereas just the statement N equals N is meaningless. So what did we have to do?
Well, we could just look at like the original rule, right? We sort of defined id refl of x to have the type x equal x. So in this case, we're just substituting z for x, aren't we?
Right. So what has to happen is that X here or N here becomes meaningless. So in order to fix it, we actually have to if it occurs in the type W, as it might in an equality type, then in order to determine the correct type of an application, we have to substitute all occurrences of X in the type W for the term A. Because X here was bound to the quantifier, whereas in this term, that binder, it's called a binder, for example, is gone. And so we have to form the substitution. And in this case, it'll produce the correct results. Because in this case, the W was this. And then if we look at, for example, W, and we substitute in place of N, Z, then what we would get is Z equals Z. If W is N equals N.
So it's a term change.
Sorry, I didn't hear that.
So basically just like a term substitution.
Right. So then this was just a quick preface, but substitution now comes into play. So we're going to have to discuss substitution. So that's the first topic that we're going to discuss today, substitution. Does anyone have any questions about this example? So I haven't discussed equality types yet. And I only went over for all very quickly last time. But I'm just giving you a general idea that substitution will come into play in the rules and predicate logic. Any questions?
Is substitution the same thing as like you're binding it, quantifying you like a specific instance identification?
Well, you're taking an instance of certain value for the quantifier. Whenever you're quantifying, you have to quantify over a variable. So, for example, in the grammar, for what a for all statement looks like, this must be a variable. And the idea is that you replace all bound occurrences of that variable in the body of W with A when forming an application to determine the correct results type. Sorry, what was your question exactly?
But, no, that's what I meant. It's binding the A. Well, X. A is bound to X. It has it's a specific instance now.
Yes.
Okay.
Yes.
Yep. Thank you for clarifying.
Right. So you should think of it as in logic, not now in programming, this as a logical statement saying that for every single natural number, that number equals itself, right? How do you use a for all statement? You use a for all statement by using any of its specific cases. A proof of for all nats n equals n should give you a proof of what z equals z and s of z equals s of z. And then I'll say it verbally and get to it back later, but the BHK interpretation of a proof of for all x in t arrow w was that it was a function that took an object of type t into a proof or into a term of type w with that substitution performed. But we'll get back to this later. I mentioned this only here because we see that in order to actually do logic, we're going to have to talk about substitution. And substitution actually has two contexts which we'll care about. There are two times we care about substitution. So substitution comes up in for all statements in universal quantification so that rule was the for all elimination rule, for example. And it also comes up in the computation rules for lambda calculus. Now, why are we doing computation? I haven't discussed that yet. So I haven't motivated yet why we would perform computations on lambdas. But really, substitution in either case is similar. So the two respective grammars are, we have expressions like for all x in t, and then we have some body w, and we'd like to take this and substitute it, well, rather, let's discuss it like this. So we can have a grammar in which T is either a for all statement of this form, or it's a propositional variable. And then we haven't discussed applications, but we can talk about substituting there. And then we have lambda calculus, in which a term, let's just do the simplest version of it, is either a variable, an abstraction, or an application. And here, there isn't exactly an analog of an application. You can't apply something to a type, but substitution is sometimes required. W might, for example, be either just a single variable, or it might be another for all statement. And then we might have to ask, well, how do you substitute when you have a for all statement, right? And then in lambda calculus, there's this idea of computation that if you have lambda x, some t, and then you have some s, and you consider this application, then the computation rule is that this should reduce to t, but with all occurrences of x replaced with s. So that's where in lambda calculus we have substitution. And then in for all statements, the rules explicitly require us to make substitutions sometimes, as happens here. Now, because lambda calculus also has this application case, there's a bit more to discuss. So we'll discuss substitution for lambda calculus. Also, lambda calculus terms are easier and quicker to write. But for all statements are easier. This includes the for all case. Any questions about that? So this is the computation rule. Now, okay, any questions? Right. So let's just see what would happen. Let's say we have a lambda calculus term, lambda xx, right? And then we can apply this to some other lambda calculus term. Just x on its own is a lambda calculus term, right? So what should that reduce to? Or, okay, let's actually say we apply it to y. What does that reduce to?
T, open bracket,
What is t?
X, not T, we do not T. Oh, we don't have a T. X, I'm sorry, X, open bracket, X, to Y.
Yes. And that is equal to, well, so if we take the expression x and we replace x with y, what should we get?
Just y.
Yes. So we haven't defined substitution yet, but that should definitely be true. Okay. Now let's say we have lambda x dot y, and we plug in z. Then what do we get?
Y open bracket x to z.
Right. And what should happen here?
Well, there's no instance of x, so it's just gonna be y.
Yes. So that suggests that if we have a variable and we're substituting for an expression, we check whether these, so always when we substitute, always, no matter what, this is going to be a variable. Why is it always going to be a variable? Well, look at the grammar for lambda calculus. This is a variable. And what we do is we always substitute for what the variable in the lambda is, the formal parameter of the lambda. So that's always a variable. In other words, variables are just names. So if you have two names, you just compare them for equality. Now, here in these cases, x and y were also variables. They don't always have to be variables, as in if the body of the lambda isn't just a variable, you're going to have a more complicated expression here. But if you have a variable and you're performing a substitution, then what you do is you compare whether these two are equal. If they are, you replace it. If they're not, you don't replace it. Right? Does that make sense to everyone?
Yes. So in terms of notation, the brackets, is it similar to, it's a rule? Like we use the brackets for rule notation?
Oh,
using it here for
there are only so many brackets in English writing. This is the notation for substitution.
Okay.
This has nothing to do with the notation by which we wrote rules.
Thank you.
I mean, if you think about it, there are also rules in brackets when you have cond statements and you write also square brackets there. So anyway, this notation is substitution. I think that's unambiguous. Right. Well, okay, let's look at this. Suppose we have something like lambda x, and then here we have x applied to y. And we're going to substitute z in. Why not? Then what do we get?
Then it's just the application x applied to y, then the bracket x to z.
Right.
And since we replace every instance of x with z, that just means application of z onto y.
But let's do it. We want to give a definition of substitution that's structurally recursive on the term. So this term is an application, right?
Yes.
So if we want to substitute into an application, what should we do? Why did you say it was zy?
That's because I checked the first term of that application, which was an x. I asked myself if x was equal to x, because there's that x that appears in the bracket. And if it is equal, I replace it with z.
Yes, and then for the next one?
And then I looked at the first of the rest of the application. I guess you can view it like a list, and then ask myself if that's equal. If not, I leave it alone, and it was not.
Right, and those two questions, they were independent, right?
Yes.
So in other words, if ever we have an application, what we really do is we just substitute into each of the body terms, right?
Yeah. So like a distributive sort of thing.
So we performed that, right?
Yes.
Does that make sense?
Yeah, like a distributive rule.
Yeah, and then if we look above, I actually, there's a typo before. When we, no, it's correct. Y remained untouched. Now x goes to z, that gets replaced with, since these two are equal, z by the previous rule, 1. And this one, x and y are different, so y remains. So here, lambda calculus terms are either variables. I'll remind everyone for the very large number of time. These are variables. These are abstractions. And what are these called?
Applications.
Yeah. So we've said how substitution works on variables. So these two cases define substitution on variables. On variables. This case defines substitution. Well, rather, I guess the first line of this equality defines substitution on applications. And finally, we have the last remaining case, which is substitution on lambdas. And this case is actually going to be tricky. So what happens if we have the following? Lambda, let's say x dot y. No, lambda x, lambda z y, lambda z x. And we want to substitute, sorry, we evaluate this on y. Okay, here we are. So what happens in here? We have the, what does this reduce to?
Well, just the lambda x dot lambda z dot x, and then the brackets.
Is it? You said lambda x. You said start with lambda x?
Yeah. I put in parentheses.
I mean, look at the previous examples that we had. Here, if we had lambda x, what did that reduce to?
Oh, sorry. Yeah. Lambda z dot x parentheses.
Yes.
And then the bracket of x to y.
Yeah. Now, what should that be?
maybe something similar, like lambda of z bracket x to y dot x bracket x to y.
Yes.
Okay, so just the z is
And that reduces to then that's equal.
so lambda z y.
Right. So that's one case. Does anyone have any questions about that?
So wait, do you also apply the bracket onto the z, like the z variable in the lambda, just in case?
No, that's actually what we're going to discuss next.
Oh, okay.
So here, x was different from z,
Yeah.
right?
Yeah, it was different.
So you're asking what happens if x is z, right?
Yeah, if z is x.
Okay, so let's actually try that. So what happens? Well, but wait, but before we go there, does anyone have any questions about these ones so far? Also, does anyone have any questions about what we're currently doing? So our goal, just to remind everyone, was that we saw, for example, that when we have for all statements, such as for all natural numbers n equals n, in order to use a for all statements, we specialize it to a specific natural number. So for example, since for all nats n equals n, we know that, for example, z equals z. Now, the proof of that in this computational interpretation should be some function that takes a specific object n and gives you a specialized proof term that n equals n. And when I say n there, I mean n could be z. Then the proof term should be of z equals z. So substitution happens in this for all elimination rule. There's another place where substitution happens, and that's in the computation rules for lambda calculus. Now, I haven't explained yet why we'd like to do computational lambda terms in a proof assistance, but the computational meaning of lambda terms, for example, as you're familiar with them in Racket, is that when you evaluate a lambda on an argument, it substitutes the argument in the body of the lambda, right?
Yeah.
This computation rule right here. Now, since if we look at what lambda calculus is, its terms are either variables, abstractions, or applications. And if we look at what for all statements are, well, they're either for all. This is, we can think of both this for all here and this lambda as being binders. In the sense that they give meaning to what x is in either case, right? And in this case, we have nothing analogous to an application. In this case, applications are actually what induce substitution. In this case, while in the previous case, it's just the rules somewhere else that might induce substitution on the body of a for all statements. But it's more general to consider substitution for lambda terms. You can think of the logical statements as just not having the application case. And later, we're actually going to have to do computation on lambdas. So we may as well do that. So we would like to define what this is. Our goal then, define this, where this is this substitution. And in order to define what it is, we basically start looking at when the substitution occurs in lambda calculus and seeing what the meaningful answers are. So for example, if you take lambda xx, that's the identity function. And so if you substitute, if you apply the identity function to y, you should get y, right? So since this reduces in a computational step to this, that suggests what substitution should be for variables. But there's another case. it's not the identity function. It's a function lambda x dot y. Now, what does y mean? Well, it doesn't mean anything at the moment. It isn't bound by the x. It occurs freely in this term, which is the notion that we'll discuss in a moment. But if you try and substitute x for z in just the variable y is not equal to x. Y is a variable. The thing that we're substituting for is always going to be a variable, because if you look at the grammar for lambda calculus, this rule substitution only occurs in the application to a lambda expression, and then what gets substituted, what you're substituting for is the variable in the lambda, and that's always a variable in well-formed lambda calculus terms. And so you just compare for equality of these two, and if they're equal, you replace it. If they're not equal, you don't replace it. So that's how substitution behaves on variables. Now, what about applications? Well, in this application, what does this function do? This function takes an argument and evaluates the argument on y, right? Does that make sense to everyone?
Yes.
So if that's the description of what this function does, then consider what happens when we plug in some z on it. Well, it should evaluate the argument z on y. And if you think about how we got to that answer, we looked at the body of this lambda, which was an application, and then we performed the substitution on both the left-hand side and the right-hand side of the application. So that's what substitution should be like when we have applications. Now, what about lambdas? Then we got to this question. And we considered this case, lambda x, lambda z x. So this is a function that takes anything, then it returns a function that takes anything, and then that returns the original thing. So if we consider this function, we apply y to it, then we should get a function that takes anything and returns y, right? Now, on the other hand, what happens if we have lambda x dot lambda x dot x? And we evaluate this on y. What is the meaning of that? Okay, well, first off, what does it reduce to in one computational step?
They mean like with the substitution rules?
Yep.
Okay, lambda x dot x, then the brackets x to y.
Yep. Now, computationally, of course, there's a question of what does this x mean? What does this x refer to? Right? If we consider the term lambda x dot x as an AST that looks like lambda x, and then x, right? So does this x refer to this x or this x?
The one that's closer to it?
Yes. So this x should refer to this x, right?
Yes.
And we can do an experiment. We can actually go into Racket. Let me just quickly, okay. Whoops. Does everyone see Racket?
Yes.
Okay. So I have intermediate student of lambda here. Let's just look at the expression. So in Racket, I'd write it like this: lambda x, x, right? So this is the lambda under consideration. Let me increase the font size. and I'll copy it so I can run it again. And let's evaluate that on 2. And then let's evaluate that on 3. So what would you expect that the answer should be?
Application of 2 on 3.
Well, in Rocket, that would produce an error, right?
Yeah.
So you're saying this will give me an error?
Well, it evaluates the 2 on the inside, so I guess.
What do you mean by evaluates the 2 on the inside?
Since you apply that lambda, which is basically a fancy identity function, onto 2,
Right.
that's going to give you 2.
Well, what you're applying to is this lambda expression, not the identity function.
Like it'll give x on the inside, and then lambda x of x.
Well, okay, let's see.
It should be
okay.
2, right?
Well, so you're saying it's going to be 2, right?
That's
okay.
my guess.
The answer is 3. Why?
Uh-huh.
Let's see. So first off, if you just had something like lambda x, the identity function, and you applied that to 2, you'd get 2, right? So the question is, if you take lambda x, and if you take this term that we had before, and you apply it to 2, well, it's going to return a lambda. It's not going to print it nicely. But let's look at the stepper. Let's look at what the stepper does when it evaluates this expression. Does everyone see the stepper? So look at this expression. It's a lambda x, and then the body of it is a lambda, right? But this lambda is a value already. And okay, well, that's immaterial. There might be free variables, but it reduces just to lambda xx. So this x right here, it referred to this x, not this x. So substitution did not happen in the body of the lambda. It instead just reduces to the identity function. This application right here produces the identity function. And then that consumes the 2, and then the next argument is the 3, and then you just have the identity function applied to 3, and that gives you 3. Any questions? So on the other hand, if we have an expression like we had before, where we had lambda x, and now let's say we change this to be y, x. Now this x refers to that x, because this is y. And now we're going to get 2. So in summary, this expression reduced to, eventually, it evaluated to 3, whereas the expression with a y for this parameter evaluated to 2. So what happens when we have a lambda and we're trying to form a substitution? and for a variable x, and the variable x coincides with what we're binding over. Then what do we get?
Do we get x, like how the x referred back to the first x, and then we got just the 2? Oh no, we got. Wait,
Well, the previous case, we had 2 applications, right? In the
Yes.
previous case, so this is in Racket, we had lambda x, then lambda, let's say, x, this Racket expression, right? And then we took that expression and we evaluated it on 2, right?
yes.
And
Yeah.
the stepper reduced that to just lambda xx. That's what we saw in the stepper.
Yeah.
So in general, if we have some lambda and we're trying to substitute and the variable that we're substituting for coincides with the formal parameter of the lambda, then what happens?
I get like the inner function.
Well, so any occurrence of x inside the body of this lambda does not refer to this x, right? It refers to either this x or another binding inside of it, right?
Yes, so it's over the.
So in other words, no possible occurrence of x inside the body of this lambda can refer to this x, right?
Okay.
So
it
there's
can't
no
refer.
substitution to be done, right?
Yeah, okay.
So that's just lambda x dot x. So substitution stops. And what we've done is we've taken this and we've compared it here, and we've taken this and we've compared it here. So the fact that these two coincide here means that substitution stops, whereas the fact that these two do not coincide means substitution continues. It's the exact opposite of the variable case. In the variable case, if they coincided, you continued, whereas if they did not coincide, you stopped, right?
Yeah.
In this case, it's the opposite. If the two variables do not coincide, you continue, whereas if they do coincide, then you stop. Are we done? Does this define substitution completely?
I would say yes, because we've considered all 3 variants of lambda calculus terms.
Yes. So that is one correct answer. The correct answer is, so right now our criterion is that there are 3 terms in lambda calculus. We said how it works for variables, we said how it works for applications, and we said how it works for lambdas. And there were 2 cases for lambdas, and they depended on whether x was equal to z. So we have defined substitution on all lambda terms. The question is, have we defined it correctly? So consider the following example. So I want to do lambda y dot x. And let's say that I want to evaluate this on y. What do I get?
Lambda y dot x, open bracket, x 2y.
Now, if I apply these cases naively, then x does not equal to y, so I substitute inside. So I'm going to write this incorrect version here. So then I'd get lambda y, x with x substituted for y, right? And what that would give me is lambda y dot y, which is the identity function. Is that right, though?
I don't think the last y should be referring to the y within the lambda because it's outside of the lambda parentheses.
Say that again.
I don't think the second y should be considered the same as the first y because the first y is in a lambda parentheses and the second y is outside of those parentheses.
That's right, but at the moment, these rules right here only look at whether the variable x is the same as this parameter. We don't look at what this is, right?
Right.
So what's, like, if we think about it computationally, what does this lambda function do? Can you describe what it does, what it should do correctly? So imagine that it's evaluated on any inputs that's different from, I mean, like this expression right here, it's roughly the same as this expression right here, right?
So suppose that we evaluate it on 5. Then it will return a function which, given any argument, returns 5.
Exactly. But the problem is if we evaluate it on y, then suddenly it's supposed to give a function that returns y, but y is a variable. It's supposed to give the variable y, right? But then suddenly what happens is that it becomes the identity function if we follow these rules. So you're right. This lambda, this should be a function. That takes any term, let's say t, and returns the function that takes anything and returns t. Let's say y, that's the function anything input to t, right? It always returns t, no matter what. Let's actually write that as underscore to t. Underscore means anything to t. And here, this is the identity function. So there's a problem. By the way, do people hear rain in my room right now? Do they? Do you hear rain? I hear a lot of rain, but Zoom might not be picking it up.
I don't
Okay,
hear
that's fine.
anything.
Then I'd prefer to keep it that way, not to put on headphones. So this problem is called variable capture. This is the variable capture problem. Now, when does it occur? So you suggested that you were on the right track before. You basically were seeing. So if we substituted this for any variable, if instead of y we put any other variable, it would work, right? The rules would be correct if instead of y we had any variable.
Could we change like the lambda variable? So could it return like lambda z dot y?
Yes,
And
that's going to be the solution. We're going to have to rename the lambda. But when do we have to rename the lambda? That's the question. When? And how do we know what variable works?
when we're substituting a symbol which matches the symbol of the lambda.
Okay, consider the following case then. Consider the case if we were taking lambda y dot x, and we wanted to substitute for x, not just the symbol y, but let's say the application y applied to z. So y applied to z is a lambda calculus term, right? Naively, what that would reduce to would be lambda y, and then you'd have y, and then you'd replace x with yz. And then we have variable capture again, right? This y should not be referring to this y, right? So that's another captured variable. So variable capture doesn't just occur with
If you put in an extra y, I feel like you put in an extra y.
Oh, right. Yeah, sorry. No, lambda y, yeah, there's an extra y. Thanks. This is just, yeah, it's just this. X got replaced with yz, and now we've captured the y. So this problem also occurs here. When does this problem occur then?
When we're substituting an application into a lambda, a lambda whose body contains the first argument of the application.
Well, so that problem, I can make it so you see how that doesn't fully describe the most general case, right? What happens if I consider, let's say zy a, this substitution, right? Then there's still variable capture, because I'll replace x with this, and this y will get captured nonetheless, right?
Yeah.
So try again. When does it occur most generally?
It's not necessarily the first argument. It could be if the symbol appears in what you're trying to substitute.
Okay, really good. So let's consider the following case. We're going to take x and we're going to replace it with lambda y. Then notice that if you actually apply the rules, we notice that x isn't the same as y, so we'd get lambda y, and then we take x and we'd replace it with lambda y. Sorry, x gets replaced with lambda y dot y. And then that gets replaced, becomes lambda y dot y. And that's fine, actually. This is okay.
True.
So what's the difference there? Why was it fine that y occurred in this expression? Why was it fine that this y occurred here?
Because the thing we're substituting contains an abstraction. Like the y is within an abstraction.
But it's not just within an abstraction. What if this abstraction instead had z here? Then we'd run into the problem, right?
Okay, it's within an abstraction that matches what we're
right.
The body.
So in other words, if we think of abstractions as sort of binders, things that bind names, then this y is bound. This occurrence of y is bound. And I should write the other example then, to also give you an idea. Lambda y dot x, and then let's consider the case x gets substituted with lambda z dot y. So while this occurrence of y is not. So if an occurrence of a variable is not bound, it is called free. This is a free occurrence of y. So then what should be the most general statement of when variable capture, this problem of variable capture occurs? So suppose we have some expression lambda y, and then we have some term t, and we're substituting y goes to some term s. Then when does variable capture occur? Oh, sorry, not y. Lambda, let's say x goes to s. That variable capture would never occur there. So assume that x occurs in t. Then when does variable capture occur?
I'm sorry, could you define variable capture again?
Okay, variable capture is the problem that we are currently experiencing. So you take a term, you substitute some term inside it, so you substitute for some variable, and what happens is that you're substituting inside of a lambda, right? So this lambda binds y, and then some y inside of this term, then you have y in here in the expression that you're substituting, and that y ends up getting captured by this lambda, whereas it should not previously have.
So
Now,
are you using
oh, go ahead.
Question? Sorry, but are you using capture in the sense of binding, in the sense of?
Oh, well, the name variable capture is the name for this problem that happens when we try and define substitution. The reason it's called that is because this binder here captures this y, which we don't want. Do you see why we do not want this result?
Wait,
So Martin, do you see in this example why this red thing is wrong?
Well, it looks like it's not what is supposed to be happening.
Well, we saw in Racket, for example, that if we looked at the function lambda, this function right here, and we substituted, oh, okay, let's actually, I haven't done variable capture in an example in Racket. Let's check that out. So in order to do a variable capture example, can anyone tell me what I should type? Tell me the example.
Lambda, oh, yeah, lambda y of x, and you apply that onto y.
Okay. Now the problem is that it's going to say that y is undefined, right? So let's say define y3 outside of the body, right?
Okay. Yeah.
So in that case, sorry, let's call this lambda lambda y, And then let's make this bound lambda x. So sorry, we take a lambda, it takes an x, and then it substitutes inside the body, which is a lambda yx, right? So here, what we want then, if we look at this function, for example, this function right here, this is the sort of the function that we were considering before. It takes anything and then returns a function that takes anything and returns the first thing, right? So for example, as before, if we put 2 in here and then 3, we get 2 back because 2 is the first thing. And so it returns a function that takes anything and returns the first thing, right?
Yeah.
So if we take this function and we apply it to y, which is defined to be 3, then what should happen is that it should return a function that takes anything and returns 3, right? So it'll return a function that takes anything and returns 3. Okay, well, if we take this function and we evaluate it on 15, then we should get 3, right?
Yeah.
Now, of course, what will happen in Racket is that if we actually look at this in the stepper, it'll replace y with the number 3. So we won't actually, because of Racket's evaluation order, it won't let a free occurrence of y happen. If we type in just y into here, it'll say, okay, if we type in z into here, it'll say this variable is not defined. So in some sense, it really relied on, that example relied on the existence of undefined variables. So I can't show it to you in the stepper. So Martin, do you see now why it's a problem? If we take this and we evaluate it on anything, it should return a function that takes anything and returns the first thing, right? Yes?
Yes.
Well, if we evaluate it on y, then it should return a function that takes anything and returns y, right?
Yes.
This function right here is the identity function. It takes anything and returns itself.
Mhm.
So if we evaluate this function on 15, it'll give us 15, right?
Yes.
We want a function that takes anything and returns y. So this answer is wrong. Do you agree?
Yes.
Okay, so now do you see why this is a problem?
Because it returns the wrong thing.
Yes, it should return some function that takes anything and returns y, whereas this function is the identity function.
Yes.
So the question is, when does variable capture occur most generally? If you have some lambda expression and you're substituting in that lambda expression something for x, let's suppose that x occurs in t, so that's the substitution actually does something. Then we're going to cause variable capture provided that what? So we looked at some examples here. In general, s doesn't just have to be a variable. If s were just a variable y, then we could check it like that. It might also be an application. Variable capture occurs here. Then it doesn't just have to be an application in which they're variables. It could be more compound. But you can also be substituting for lambdas. Now, this case, we encountered variable capture, whereas in this case, we did not. And we said that this occurrence of y in this lambda term was bound, whereas this occurrence of y was free. So most generally, if we're substituting s for x into a lambda with y as its outside binder, we might have variable capture provided what?
the example we've seen is that if S is lambda y dot y, then variable capture occurs.
Well, no, it doesn't if it's lambda y dot y,
Oh, really?
because this y is bound to this y. So the answer that you get is lambda y, y, right? This y
Yeah.
refers to this y.
Okay.
So it's not a problem. It's only if you have lambda z dot y, in which case this occurrence of y is free because it's not bound by z. It's not bound in this term. So this term is said to have a free occurrence of y. Whereas this term does not have a free occurrence of y. So we need to check what? So it's something about the term s, right? And something about y.
Lambda something dot something that contains y.
Well, here's the thing. I could then try. So try and make your own counterexample to this. What if it's an application z applied to lambda zy? It doesn't have to be a lambda at the top level for this problem to occur, right? It can be an arbitrarily complicated lambda expression that you're substituting in. Do you see?
True. Yeah.
So I like that we went through these examples. It's actually, this is really good. Substitution is very tricky to define. And then you always think that you have it, and then you keep coming up with examples. So if I ask you to do this on your own, you would be convinced that you'd have a correct answer at least like 10 different stages before you realize that, oh no, I have to adjust this. It's substitution. A lot of famous logicians made mistakes about defining substitution. But I understand it, so I can tell you where all the mistakes can occur. So
Thanks.
So what are we really checking? So why is this one an issue? Why does this example cause variable capture? Let's answer that question.
Because the expression that we are substituting in has a free occurrence of y.
Yes, perfect. So this expression has y occurring freely. Whereas if there are no free occurrences of y, then there are no free occurrences of y to get captured, right? So the only thing that can get captured are free occurrences of y. Does that make sense? Here's an example of an occurrence of y that's not free. It refers to this. So if we're going to substitute this inside of a lambda that has y, that y can't possibly refer to this occurrence of y because it's already bound. So in other words, when we're trying to substitute x for s inside lambda y, we need to check what? Whether s has what?
Whether it's bound.
Whether what is bound. S is a expression, a lambda term.
Has a free occurrence of y.
Yes. That is the correct answer. So the variable capture problem occurs when the term that we're substituting for has a free occurrence of y. So we should define what it means for the term to have a free occurrence of y. So we can define this in terms of sets. Let's define a function. So set just keeps track of membership. They're the things that I should have talked about in this class, but for which we didn't have time. Define, or you know what? Let's actually do it like this. Define here, free in, no sets. Free in. So this is going to be some function. And what it's going to take is it's going to take a variable, and it's going to take a term, and it's going to return a Boolean. So for example, free in. So variables, I'm going to write variables like this. Free in x in the term, let's say lambda, or free in x in the term x should return false. Except I'm going to do it in Proust. In Proust, variables are quoted, right? So this should return false. Sorry, this should return true, right? X is free in x, right? So in general, how should this function be defined? It should be structurally recursive on the term, right? So if you have a variable, x, and then you have some variable, some term t. If t is a variable, then what?
Returns true.
Not necessarily. That variable might be a different one.
Huh.
Equal xt.
Yes. So we can sort of define this.
Also, wouldn't you quote the t?
T is a term, right? So t is going to be, okay. I'm not defining, I'm doing this in half bracket. I should write a variable here as something different. So if I wanted to define it in bracket, I'd have, let's say v. V is the variable, right? So if I'm defining this, so v is a variable, and then I define this as a match. And then I'd match what the term was, right? And let's assume that terms are Proust expressions, right? So for example, if t is a symbol, you could write symbol t. Oh, sorry, symbol x. So x is now it's going to match. So x is now t is a symbol, and that symbol is x, or it's bound to the variable x. Then what do you do? Then what do you return? So if t is a symbol and that symbol is given the name x, x might be, for example, symbol y. So x is a name for a symbol, and then v is also a name for a symbol. Then what do you do to determine if v is free in t?
Equal xv.
Yes. So that handles this case. Now let's say that our expression is an abstraction. So we'd say in Proust, that would be a lambda struct, right? And then we'd have a variable. And then we'd have a body. Let's call that body E. Then what do you do?
I need to write condition.
I don't hear.
Write the condition.
Right. So let's write it as an if statement, actually. So what do you check? What are you checking?
Equal xv.
Yep. Then what? If they are equal.
Then free in ve, right?
Are you sure? So if you have lambda x dot something, whatever, is x free in this expression? Can x possibly be free in this?
It's not. So
Right. So if the binder is equal to x, then what do we return?
I should return false.
Yes. And if the binder is not equal to x, then what do you do?
Then I do free in.
Yes. So we're still checking if free is free in something, and now we're looking at the expression E. So that closes this, and that closes the lambda case, right?
Yes.
Then what about the final case, where we have an application? Let's call it E1 and E2. Then what?
We do an if statement, and we check free in ve1, something like that.
And if it's false, then what?
If it's false, then we return false. No, it has to be false in both cases. So
Yes.
we check free in xe2.
Yes. Now, if you have two statements, both of which return a Boolean, and you want to ensure that both of them are true, then the bracket has OR operations, right? So you could write this as an OR statement. And what are the two things that one of which at least must be true?
Free in v e1.
X, E1.
X.
Sorry, not X, V. Yes, thank you. Well, you were right. I don't know. So I made mistakes here as well then. It's free in V, right?
Yeah.
Yeah, all recursive calls should have V. Okay, and the second branch is?
Free in ve2.
Yeah. So if X occurs in if you look at an application, then if X is free in either the left-hand side or the right-hand side, then there is some free occurrence of X in the expression. So now I close the match statement, and now I close the define. So actually, this racket program is a complete implementation of free in. V should be a symbol, and then T should be some lambda expression in Proust terms. The structures that Proust has for applications are app, and then for lambdas is lambda. So that's a definition of free in written in Racket. We developed it. Notice how nice match statements are. Do you see how hard this would be? Well, more annoying to write with cond. But here we can just do this. And it's great, right? So that is how we check whether a certain variable is free in a term. And so if it's not if it's not free in the term, then lambda capture can't possibly happen, right? Does that make sense?
Yes.
But on the other hand, what else do we do? So let's actually summarize what our rules are right now for lambdas. So our rules are, let's suppose that we have some lambda expression. Let's say lambda x dot t. And what we're trying to do is substitute, let's say, x goes to s. Then what's the result here?
We would substitute x with another variable.
But look, x
The,
is
the one
argument.
after lambda. Yeah,
Hmm?
that one. Probably z. I mean,
Let's look actually at the examples we had before. So consider the first case. Right, the second case. In the second case, right? In this case right here, lambda x, x, right? So what happens when we try and substitute x for y in the body of this expression? What does this x refer to? It refers to this binder, right? So there can't be any possible free occurrences of x. We're substituting for free occurrences of x with y, right?
yes.
So in other words, when we have lambda x something and we try and substitute for x, then what happens?
Then we just get lambda x dot x.
Right, the original thing. So substitution doesn't do anything, right? Okay,
Yeah.
so going back here, if we're working with the case in which the variable of substitution matches the binder, then what?
Then it's the original input, lambda x dot.
Now, on the other hand, if we have lambda x dot t, and now we have y goes to s, now here x does not equal to y. Then let's suppose that let's suppose x does not equal to y and x does not occur freely in S. Which means if we call free in on, let's say, so x, I want to check x and s, I get false. Then what? Then I know for a fact that variable capture does not occur, right? And what can I do?
Then we substitute t with
well, we substitute in t, right?
Yeah, in t with y replaced.
Yes.
With s.
And now in the final case, if x does occur freely in y, freely in s, then what should we do? So someone said it before. What do we need to do?
Lambda
is it
the new variable dot
We should, rename x, right?
right.
So we should take x and rename it with something else. Let's say z. Then what do we have to do with the body of t after we've renamed x to z?
Substitute y in for s. Yeah.
Y in for s, but what about occurrences of x that we had before?
We substitute x with z, then
Yes.
y with
Oh
z.
yeah. Okay.
So in order to rename x with z, we need to change it in the binder and in the body. And then we substitute in this expression, or I guess we can write it like this. If we want to write it structurally recursively, we can write it like this. First that, and then y goes to s, right? But now what condition does z have to satisfy? Where z is...
Z cannot be free in S.
That is not free in S. Yes, that's what we wanted. That was one of the issues that we wanted to solve. But what other issue could we introduce by choosing a Z, another Z? There's another type of variable capture that can occur, right? Look at the term t. So consider, for example, the following expression. I'm going to write this in blue. If we have lambda, let's say, okay, so lambda x, lambda y x, right? Let's take this guy. I'm not going to write superfluous parentheses and substitute in it. Oh, let's do something more complicated. Like this. So this takes something and then returns a function that takes anything and returns the first thing applied to z. And let's evaluate this on y, right? So the issue is that y occurs freely in the thing that for which we're substituting, right? So what does this get replaced with, first off? What are we doing? What do I write here? Don't think too much. Just what do I write here?
It's 2y.
X, yes, gets replaced with y. Now the issue is I look at y here and I look at s, which is y. Y occurs freely in s, which is y, right? So I need to rename y, right? So let's say I choose to rename it z. So I'm going to write this in red to indicate why it's wrong. I choose to rename this as z. But then the problem is that here inside of the body, I've now captured z, right? So I now have the same variable capture problem. Do you see why this is wrong? To have chosen to rename it z? So here z was occurring freely inside t. And if we chose to rename y to z, then we've captured z, right? So we need to see that z is not free in S and also what?
That it's not free in T.
Yes, that is not free in S or T. So that is how you correctly define substitution. You have to go through all of this work. Substitution is much trickier than you would think. Like you would not think that substitution is this hard. Yes, substitution is this hard. It's actually one of the most surprising, tricky things in logic. So in summary, our rules are, okay, so this is what happens when we're substituting for a lambda, right? And I can write the other cases. So this is substituting for a lambda. There are 3 cases, right? Here's case 1, here's case 2, and here's case 3. Or rather, case 2 begins with this, and case 3 begins with here. So this is substituting inside, substituting in a lambda. In an abstraction. And then to handle the other cases, then if for variables, there were 2 cases for substituting for variables, right? The first was that if we had x and we were substituting x goes to s, then what do we get? Well, don't think too much. What are the answers?
S for the first one
Yes. And
and Y for the second one.
yes. So this is substitution into, this is the variable case. So I can, I guess, write it here. This is abstraction case. This is the variable case. And then the application case was actually the shortest to define. If we had, let's say, T1 applied to T2, and we wanted to substitute X for S, then what did we get?
Oh, you get T1, X
With-
substitute S, and
Yep.
T2, X substitute S.
So the complete definition of substitution involves all of this, and it also involves defining what free in is. What do people think about that? How do you like them apples?
That was hard.
Yes. And you can see why a lot of people who were to be the first people to do this got it wrong repeatedly. I mentioned on the
How do we know
exam, for
that we're
example,
right and that? Yeah, how do we know that we're right?
how do we know that we're right? Well, if you actually looked up Probocker's notes, the older version did not actually include this case or T. So there was actually a mistake, which I spotted. And also we're making a definition. So it's hard to define what the correctness of a definition is. So we actually don't know if we're right. And I think we should actually be really suspicious because mistakes might have come up. So Prabhakar presented this in the notes and he didn't have the free in T case. Yes, we don't know if we're right. The criterion for rightness is that we saw that we were wrong in previous cases because we have an intuitive idea of what substitution should behave and how it should behave. And we saw that we got into problems if we defined it naively. In order to show that this definition is wrong, you'd have to show me a case in which substitution didn't behave in the way that my intuition would expect. But we don't know if we're right. That's the problem. And that really can't be solved because we're making a definition. So it's hard to give a criterion for a definition to be correct. It's just supposed to capture the intuition. Okay, but so at the same time, substitution should be something that's intuitive. We all have an intuitive idea of how substitution works. It just turns out that it's much harder than we expected. And you have to do this once in your life. But once you've done it, you've done it. Now, okay, so notice that substitution might cause variable renaming, right? And so if we actually look at terms, we should identify terms. Plus, we didn't exactly say, we said that Z should be chosen to not be free in either of these, but we didn't say what Z to choose. So really, we should allow all terms to be considered equal up to renaming of variables. So for example, lambda x dot x and lambda y dot y are both the identity function. While lambda x dot y is not, and is different from lambda y dot x. So we would like to identify both of these, especially since substitution involves renaming binders. And the way in which we identify them is called alpha equivalence. So this is alpha equivalence. Which means treating terms as equal up to renaming bound variables. Terms are defined up to renaming bound variables. And this is done in a way that avoids lambda capture. Sorry, avoiding variable capture, while avoiding capture. So for example, let's write the following thing. Let's just write this notation I've made up on the spots. Let's write 3 bars like a congruence and an alpha as a subscript. So lambda xx is alpha equivalent to lambda yy, right? We do this by renaming x. Whereas lambda x dot y is not alpha equivalent to lambda y dot y. So here we changed x to y, but we caused variable capture, and these two terms should not be alpha equivalents. Does that notion make sense? And then, for example, in logic, we're going to have things like for all x in t, let's say x equals x. So that's a type. And then this type should be alpha equivalence to the logical statement for all y in t. Y equals y. So this is actually something that we saw when we had logical statements. If we had for all, we could rename the bound variable for all. So for example, for all nats n plus z n equals n is the same logical statement as for all nats m plus zm equals m. And you can see how variable capture can occur even here. In this sentence, there's no possibility of variable capture because there aren't quantifiers. However, if you had nested quantifiers, then you couldn't rename the outer quantifier freely without causing variable capture. As a very simple example, if you have for all nats n and then for all nats m, if you rename n to m, then the previous occurrences of n will get bound to the innermost quantifier. For example, we wrote for all nats n and m, for all nats n, for all nats m. Plus nm equals plus mn. Right? This is not equivalence to for all nats n, let's say m, for all nats m, plus mm equals plus mm. So even in logic, you actually have variable capture occurring. Because in this statement, as we had before, if we were trying to rename this, then we might have what we renamed being captured by this quantifier. And the other thing that could happen is if we were instead renaming this statement, then we could rename it in a way that it's captured by this outer quantifier. So even in logic, you actually have the notions of variable capture. So that problem doesn't just come up in lambda calculus. It comes up in substitution in the way that you're used to doing it in high school mathematics. High school substitution is also prone to variable capture. Okay, so that was a lot of material right there. And let's take a break for now. But no, let's first, I'll take any questions and then we can take a break.
I have a quick question about PGA.
Yep.
Could you explain a little bit more about how I can print
Right.
that additional test
Thank you.
case?
This is very important because there's currently a PG8 typo in the problem statement, and I needed to actually, okay, for PG8, I'll extend the deadline to be due tomorrow. I'll extend the deadline by a day. For PG8, you should print let's say T implies contradiction as not T. And then the way that you recognize this case is that, for example, you have the following case in pretty print type. You have the case for example, that would be an arrow, right? And then you'd have, let's say, some you'd have arrow E1, E2, right? That would be a case in your match. Yes, you previously have this, yes? So
Yeah.
above it.
Professor, I'm defining printing types, so it should be, I mean, T something, like T1, T2.
Well,
Expression.
for pretty printing types, arrow is a thing that occurs, right? Arrow is a type.
Yeah.
So in pretty print type, there's a match statement, and then it goes over all of the possible types. One of them is arrow, right?
Yes.
Oh, well, I guess I call the variables E1, E2. It might be better to call them T1, T2. You're right.
Just to be consistent with the other cases.
Yes. What are they actually called in the program? Are they called T and W? Or no, they're called TT and TW, right?
Yeah.
This is what they're called. So in this case, you put above this case. Above is very important. You add what? What do you add? You tell me.
Arrow T call. Contradiction.
Yes, and then your personal structure, whatever structure you have for this. So this should be, this is your AST node for contradiction. So the name cond, for example, or cont, or con, that's something that you defined, right? That's your name. And then you should print this as printf. Then you'd write the string, so it would be negation, and then you, well, how do you write it? Is it percent A? No, tilde A?
Tilde.
Yeah. And then you recursively call pretty print type on TT, right? So you add this case, and it's very important that this case be above this case, because otherwise this case will get matched. What you want is, this is a special instance of TW, right? This variable TW matches anything. Whereas here, this is a specific thing. So if this case fails, then it'll match this case. If that case is below this case, then whenever this case would get matched, so would this case. So that's why it's very important that it be above, right?
Yeah,
and when I wrote should, I should write must. A marmoset will reject submissions that don't have this. Okay, sorry, question?
oh, I said the first time I didn't realize I should put the second thing on first, and I debug, spend lots of time on debug it.
Yes. Yeah, this is actually a very important lesson to learn. I sort of warned that this might be a problem on the first programming assignment, that you should be very careful about the order of cases in your match statement, but this happens in a lot of contexts. So that it's very important to note that match is prone to errors if you reorder the cases wrong, because some cases might be more general than others. So that's a good thing to learn. Okay, any other questions, or let's take a break? Any other before that?
Yeah. So for PG7, you mentioned that the V rules, that they're type synthesis, but aren't they type checking because they're going from the expression to the type?
Let's see, I have the rules written down here. No, because so it's or, right? So if you have a term like or intro 0, sorry, did I say that there's synthesis in the assignment?
Yeah, you said there was synthesis in the assignment.
And then did I write checking rules after writing that there's synthesis rules?
Yeah, you wrote leftward facing arrows.
Okay, yeah, thanks. That's a typo. They are checking rules. I should correct that. So you're adding 3 cases to type checking.
Okay, and also
for the PG7, right?
Yeah. So in the email you sent me, do I still look at the application, because that was in type synthesis, but we're looking at type checking now?
Yes. But nonetheless, if you look at or elimination, there's a synthesis involved in the premises, right?
Yes, there is.
So, and that premises, if you actually look at the rule, actually, this is going to be relevant for what we're doing after the break, when we discuss how computation comes into things. So that premises, we were trying to type on or elimination. And then there were 3 branches to it, D, F, and G. So let's say this type checks to V, provided what?
Provided that in the first branch, it's that the context yields D synthesizes to T or W.
Right. So D synthesizes to V or W. And then?
And then it's the context yields F, which is checked to by T to V.
Oh, right. I wrote V here. I want to write T, right? T or W.
Oh, yeah.
G type checks to T to, sorry, W to V.
W.
Now, if you look at this, what's happening is the synthesis call doesn't involve this type. The synthesis call just happens with the term and the context, right?
Yeah, it only takes in those arguments, those 2
Then
arguments.
whatever is returned, you have to pattern match it against an OR type, right?
Okay.
So for example, if you looked at the application rule, if you looked at implication elimination, if you had F applied to G, we could synthesize from this the type W provided what?
The type W provide that there's also, in the context yields, F synthesizes to T to W, and
Yes.
also the context where G synthesizes to T.
Oh, sorry, it's not synthesis. I shouldn't write G, I should write A. But A synthesizes or type checks?
Type checks.
Right, to
T.
Right. So what happens here is then, again, you call synthesis on this. And then if you actually look at the implementation has a match statement against the result of synthesis to an arrow type. Here you have to take the result of the synthesis and match it to a OR type. And then once you if that match succeeds, then you know what T is and you know what W is, right? Here you have a synthesis, so you know what V is as well, right? And then you know what to type check against because you know what T, W, and V are. So now you can fill the blanks in. Here you need to fill the blank in from here, right?
Yeah.
So
So
that's
each-
why it's really nice that this rule has checking at the bottom, because this V is used to fill in that blank V here, right?
Yeah. Oh. Okay. So instead of VA, just do like type synth of VLM. DF.
Well, you have to, the first thing that you have to do is you have to match it against, so that match statement will define, let's say, TT and TW, and then let's call this type. So you're originally doing type checking, right?
Yes.
So let's say this is type. Then here you would type check against arrow TT type, right? And this you would type check against arrow
Right.
TW type.
Okay. So that would take care of this unbounded identifier error, like you just
Exactly.
type in V.
Because you were matching against V and you weren't binding TT and TW. Your unbound identifiers were the things that you should have produced out of that match statement for the results of this synthesis.
Okay. Okay. Thank you. Yes.
No worries. Any other questions?
Yeah, sorry, this should be quick. So for the
Mhm.
last question, PG8, I
Yep.
implemented what you said, and the last test case still doesn't work. So does that test case have to do with how we're printing or something else?
I can check during the break.
Thank you.
Okay. So let's take a break until 3:45. Resume at 3:45. And I'll check the case first. I can tell you that the last case involves, are you still there?
Yes.
Okay. The last case involves two knots. I suspect that you didn't make this recursive call correctly.
Thank you. Thank you.
Okay, that should be that. Okay, I'm also taking a break now. Okay, we're all back. Right, does anyone have any more questions?
I have a quick one.
Go ahead.
So after I added the case that prints out the correct implication for A implies contradiction that
Right.
gives negative not A. If I said set task, then the third question say of proof PF7, what it gives me is not A, which I think would be more difficult to solve than the original question. Is that what's
Well,
intended?
so if you think about it, you can restrict to a version of logic that at first all user-defined types have not in them. And then nots are desugared to implies contradiction. So the last test case I checked, it should print as not something. That gets desugared to, there are two arrows in it, right?
Yes.
But in writing not, when you pretty print terms, it's quicker.
Yes.
Okay, I guess I didn't understand your question. What was your question exactly?
So if I don't have that statement, what it gives me would be something implies something. That was what I've seen for the previous cases where I don't have the not.
You'd get, so not T would be T implies contradiction. You
Yeah,
should
but
print
there are more
as,
terms associated with it, like what it has A or B or something else. But then the original statement was reduced to just have A.
what do you mean?
Say the original statement was
You
A
mean T?
implies B or C implies B implies contradiction, implies C implies contradiction, implies A implies contradiction. And if I set that to be the task,
Oh, I see. You're talking about associativity of brackets, right? So well, TT should only match a single expression, right? It shouldn't match a list of expressions. When you have the case where you have implies and error, are you talking about implications without brackets? The way that it automatically associates them?
yeah, I think so.
Well, okay. This shouldn't bring up a problem there. Can you give me an example in which it would bring up a problem?
I mean, it's just I think personally it's more difficult to prove it.
Oh,
because
but the statement not it means the same thing as this statement. It's just how you write it. It's not more difficult to prove in any way. These two statements mean the same thing, literally.
so I should think of not as an implication
Yes,
where I refine it with lambda.
exactly.
I see. Okay.
So oh right, but then I see what you're saying. You're saying that when you're interacting with Proust, then it's you have a worse interaction. Okay, I see exactly what you mean now. I see. Yes. So you're saying that doing this makes Proust less helpful for interaction, for building up things piece by piece. Okay, your objection is valid.
Because what I expect to see is more of an expanded version of the original statement.
Right. You have a valid objection. But my test cases right now, as it's live on Marmoset, want you to print this.
Okay.
So the advantage is it's short. The disadvantage, as you've exactly correctly pointed out, is that it's less helpful when you're building things.
That's fair enough.
Right. So that's not exactly an answer. That's me just saying that you have a point, but I'm not changing the test cases. But good point.
Okay. A quick question. Does the method printf, is method printf different from the method format, which is used
Oh, is
in
that
the-
what's that's what's used in there?
Yeah.
Format.
Okay, so
Okay.
are they different?
I think that one of them has an optional argument in which you can specify the stream to which you're printing, whereas format always just returns a string. Actually, printf might return to printf always, format always returns a string, right? And strings appear in blue with quotation marks. But if you print something, it'll appear in purple. Not as a string, but as an actual output.
Okay.
So I'm think that printf will actually not return a string, but it will output to a string. So I actually want format. Printf was wrong. But you can try that yourself. See what printf does. At the end, you can see Proust, and it's producing purple text, right? When it writes, at least in my inverted color scheme, it looks purple. Strings look different from output, right?
Yeah. Yeah. Yeah, they are purple indeed.
Yeah. Any more questions? Well, going through substitution before was hard, so that actually that took a lot of energy and concentration from me. Sort of more than I expected. Let's see if I can do the next section in peak concentration. Right, so where alpha equivalence will come in is, for example, before we had the turn rule. And what was the definition of the turn rule? Well, what did we have? Sorry, the variable rule, not the turn rule, the variable rule. No, I want the turn rule. I do want the turn rule. So let's say we're trying to type check, right? So let's say we have some expression t, and we're trying to type check it to some type t, right? Then what are we allowed to do?
We can see if little t type synthesizes capital T.
Yes. And then what do we have to check? It synthesizes, let's say, W, and then what do we check?
That W is equal to T.
Yes. That T is equivalent to W, right? So this was the turn rule. Now, if T is an for all type, if it's, for example, for all X in nats, n equals n. And we synthesize the type for all n in nats. This should be X equals X. And we synthesize this type, then or should these two be equivalents?
Yes, because they're alpha equivalent.
Yes. So we see that these should be equivalents. So in other words, this should consider alpha equivalence. So before, when we just had types where we just had A implies B implies A, then we could just check for equality. We could just check using equal. But when we have for all and we have quantified variables, this should at least detect equivalence, because these two types, well, these two types classify the same terms. If you think about a proof of this, that term, it can be a lambda, but the lambda can be named anything. It doesn't have to be lambda x. So these two types classify the same terms. Now you could say the same thing about the types A implies A and B implies B. But we still don't consider these equal. However, as we'll see, we won't even consider these to be types in our new system for all logic, because we won't have type variables. We'll have just variables. Anyway, so that's just a preview. Alpha equivalence is going to be relevant in the least, because when we could compare for type equality with universal types, we should allow renaming. And that's this equivalence operation happens in the term rule. And we're going to see that actually a lot happens here, not just alpha equivalence. We're actually going to have to look at computation as well. So that's just a quick preview. Anyone have any questions? Right. So let's get back to where we were before. So we considered for all statements, and this is called universal quantification. And what we said is that in our grammar, okay, before that, so in predicate logic, we are going to want types like let's say z equals z. So there are terms and types. What we also want to allow, we will also allow things like lambda, let's say capital X, and then arrows are implication. So we can form something like this returns X implies X. And then if we imply this to something like nats, this should computationally reduce to nats implies nats, or nats to nats. So we also want to allow ways to form propositions from variables. We can write something like lambda n dot n equals n. And then this is a function that if you give it something like 5, the result is 5 equals 5. And that's a type. So we also want to allow terms which return types and which can be applied to other terms to yield types. In other words, we are going to mix terms and types very liberally. What we had before is we had, so for example, parse type and parse expression. Parse expr and parse type. And two separate grammars for terms and types. No, we are going to abandon this. We are going to combine them. Which is going to cause a lot of issues. So for example, if you just looked at the previous one, for propositional logic, terms were very different from types. And if we were trying to type check something, we could be sure that the thing on the right-hand side of the type check was actually a type. If we had a single grammar for terms and types, then that wouldn't be guaranteed by the grammar on its own. So it's a very inferior design to mix terms and types if you're allowed to not mix terms and types. But unfortunately, really, we're going to go about it by mixing them. I really try to avoid mixing them, but it actually becomes much more complicated than it is if you mix them. So we're now going to introduce a new grammar. And the current grammar is just going to have it's just going to have expressions. So an expression is either a variable or it's and this is either a propositional variable or a lambda variable. I'll write it with a lowercase x. Or it's a lambda. Or it's an application. Or it's an arrow. Or it's a universal quantification. So here, all of them are mixed. So right now, this grammar allows you to write, allows you to form things like for all x in, what would be a very bad thing to quantify x over?
X.
Right. Yeah. Yeah, that's another, yes. However, x could be meaningful elsewhere. What's x might mean something like not. What is 100% certainly meaningless? Okay, so we could form something like this. Let's say, so we don't have equality types, but let's just say let's say we have equality types. Okay, so that's bad, but what's even worse? For all x ranging over, what's type of expression here definitely does not look like a type?
Lambda x.
Yes.
Not x.
Lambda, let's say lambda xx. Okay, this is bad. This is definitely bad. This looks like nonsense. Because this looks like x has type lambda, but lambda really definitely is not a type. So not everything makes sense as a type. Not all EXPRs are meaningful terms or types. And so we should actually introduce something into our expression language that says that something is a meaningful type. And this is going to be the constant type. So for example, we can consider the expression. So type is going to be the type of types. And we are going to define what it means to type check something as being a type. So for example, and here's the most mind-blowing thing. We will also allow quantification over all types. So we will allow you to quantify over all possible types. If you know anything about set theory, this very much sounds like quantifying over all sets. And it's scary, but it makes sense in type theory. You're definitely not allowed to do this in set theory. If you think of types as sort of sets of their terms, then this is sort of like quantifying over all sets. Except we're allowed to do it in type theory because we're much more careful about our foundations. Well, set theory isn't less careful about its foundations, but types theory has a foundation in which you are allowed to quantify over all types, and it makes sense. Right.
When you
Okay.
say that type is the type of types, what does that mean?
So what are some examples of types? We're also going to say that type has type. And this is a very, in the empty context, type has type. This is a questionable decision. And we'll come back to this decision at the end of the course. Before, when we looked at this quantifying statement, we said that this statement did not make sense, right? You were quantifying over a lambda. Overall, what does it mean that X has type lambda? Lambda is definitely not a type, right?
Right.
Now, so what is a type? Well, here's one rule that says that something is a type. Type is a type, right?
Sure.
We can also have things like we don't have them yet, but not. Not is going to be a type when we introduce nots. So from these two statements, if we look then at a universal quantification for all X in, in what goes here should be a type. In other words, we can consider, for example, for all X in type. Type is a type. That's what the first sentence says. And then we can, what will this form? Well, we need to put some expression. Let's consider the expression. Expressions can also be types. So we can form arrows, right? So we can consider for all X in type, X implies X, right? And so the following for all statement should make sense as a type in its own right.
Okay.
Right. Now, in other words, whereas this statement for all X in lambda, let's say X dot X, anything, should be meaningless. So I'll write a big cross here. This is meaningless. And what's the criterion by which it's meaningless? The problem is that this lambda expression isn't a type on its own. Whereas if we had something like for all x in nats, let's say x equals x, then that does make sense as a type. And the difference is that here type is a type and nat is a type, whereas this is not a type. Types are things in which it makes sense to ask whether something is a term of that type. So if you think of types as logical statements, then it makes sense to ask whether a logical statement has a proof, right? It does not make sense to ask whether a program has a proof. It does not make sense to ask whether a lambda has a proof. A lambda is not something which can be proven or not. It's just a lambda, right?
Right.
Now you can say natural numbers are not something that you can be proven, but natural numbers have terms. Each natural number is going to be a term of the type nat. So nat is a type in the sense that it defines a collection of terms, of nat terms. Similarly, type is a type. Types, the terms of type are all possible types. So type classifies terms, nat classifies terms. Lambdas do not classify terms. So a type means something that classifies terms. Types classify terms. Types, i.e. things that classify terms. So in other words, for each of these language constructs, for example, for all statements should be types. But in order for them to be sensical as types, some rules have to be satisfied. So in other words, let's look at the following statement. Let's suppose that in some context gamma, we consider the expression for all x. So x is always going to be a variable. And then we're going to have some t here. And then we're going to have, let's say, some w here. So that should, let's say, type synthesis, it should synthesize to the type, provided that certain hypotheses holds. So in other words, when is a for all statement a meaningful type? What should the conditions for this to be a meaningful type be? Well,
X shouldn't be a lambda.
but what should be a lambda? T shouldn't be a lambda?
I thought X.
X is a variable.
We should,
No matter what, X is a variable. That's in the grammar.
yep. Okay. T.
T shouldn't be what?
Well, we shouldn't have a lambda on the left side of
Okay. We
Mhm.
also shouldn't have an application, right?
True.
Also, if we have a for all statement, then that for all statement shouldn't have a lambda in its T position, right?
Yes.
But also, if in that T position there's another for all statement, then you have to check that that for all statement is also well formed, right?
Yes.
So in general, you're performing some recursive computation there. What is that recursive computation? What do we want to check about T?
That a lambda doesn't type check to T.
Well, T can be type to type, and then lambda does type check to type to type.
True.
So for example, lambda x dot x should type check to type to type. It's the identity function. It takes a type and returns the same type. So lambdas can type check to types. And then type to type itself has type type. But notice that lambda x dot x does not type check to type. It type checks to a type, but that type is not type.
Wait, what are the different variants for types? So we have like arrows, ands,
For
or
alls.
for
And then also variables might be types if in the context they're types, right?
yes.
So for example, in this statement, if you went into the body, then x would be necessarily, well, x would be a term of some type. But if we had t is a type, and then x was a term of type, then x would itself be a type, right? So variables can also be types if in the context their type is type.
Yes.
In short, this discussion has the word type said a lot. Okay, but that's a joke. So what do we need to know about T, right? We need to know something about T. T can't be a lambda. What should T be? What should be true about T? T should type check to what type? So for example, lambdas here, they type check to type, and we don't want a lambda. But lambdas certainly do not type check to type.
Can
So-
we use arrow?
Sorry, what?
Can we use arrow? Is that possible?
No, well, we're trying to write down what the rules are. There's no errors in the rules for here. What the question is, when is this a type? When does this expression at the bottom define a type?
When T type checks to type.
Yes, so T should type check to type. Now, if T type checks to type, right, then we need to look at W. And now W might have X occurring in it, right? So we're going to take our context and we're going to add X to it. And what should the binding on X be? So to give an example, consider the following type. For all, let's say X in type. For all types X, I'm going to form the statement for all X in lambda X. And then something like X. So here in the body of the for all statement, we have something that does not make sense, right? So this should not be a type because this expression right here does not make sense. So we need to check W recursively, right? But on the other hand, if we, well, okay, I guess I'll call this, let's say for all capital A in type. If instead of that, we looked at the inside of the lambda and we had for all x in A, for all terms of A, then that makes sense. But that would not make sense if we didn't know that A stood for some type. So we had to add x to our context, right? So this example is actually good. Let's look at this example. I want to spend some time on it. So let me actually write it down below. So we're considering the expression for all, let's say A in type, for all types A. Or even something simpler, for all types AA, right? This makes sense, yes? This is, this says that for all types, consider the type A. A term of this type would be, for example, lambda x dot x is a term of this type. And then so why does A make sense here? Oh, okay, sorry. I don't know what people are thinking. Let's just look at, let's look at the process of type checking this term. So we don't know what the condition is here yet. We look at the term gamma. So let's look at the empty context, and let's look at the expression for all A in type A. And let's say we try and run type synthesis on this, right? So here the rule says for the first premises, what should we check? According to the rule above, what do we do? What's the first thing that we check?
Whether type checks to type.
Yep. And I guess then the rule that we have for that is that, I'll write it here. In any context, type synthesizes type. So that's the rule for type. I guess we'd switch to synthesis mode if we were writing it in bidirectional form. And type does indeed type synthesize to type, and these are equal. So we use the turn rule there. And this thing is an axiom by that rule. Okay, now that we've checked type, what do we need to check? Because the body of this for all might be meaningless, right? We saw an example in which it is meaningless. You can write, for example, the expression for all A in type, and then it's easy to form meaningless expressions. We can form an expression like for all x in lambda x dot x, right? That's meaningless. So that's problematic. So we do need to check what this W is, right? So in this case, the W is A. So we want to check A. We want to do something with A.
do we just want to check whether A type checks to type also?
Actually, we can consider statements like for all A n in nats. Oh, yes, yes, yes. We do want to check exactly. So if we want to prove a for all statement, then what is the BHK interpretation? It should be that given an object A of type, it should be a term of it should be a function that transforms that object into a proof of the right-hand side after substitution, right? And to be a proof of the right-hand side means that the right-hand side should be something that classifies terms. So we would also like to type check this against type. But A here does not make sense on its own, right? What should we do? We should add A to the context, right? And what should the binding on A be?
Type.
Yes. So in general, in order to see that a for all statement is a type, what we need is that T type checks to type, and in context gamma with what?
That double that W
Is the type T?
Well, what's the context? What do I add to my context? X has what?
Type T.
Type T. That what?
Oh yeah, T.
W?
Then W type checks to type.
Type. Right? So this is the rule for a for all statement being a meaningful type. Now, we can also have for all statements in which we're quantifying over nats. And then the thing that would get added to the context is that something has type nat. So for example, in the statement above here, let's say I use n, little n for nats. Little n is more conventional for things which are clearly terms. For all n in nats. Then what I would add to my context is that n is has type nat, not that n has type. And then if I wrote for all n in nats, something like just n, that would be a meaningless statement, because how do you prove a specific natural number? A specific natural number is not a type. So this statement is meaningless as well. So in order for a for all statement to be a well-formed type, both T has to type check to type, and also in the context in which X has been given type T, W should type check to type. But if that happens, then we are able to synthesize the type. So this is the typing rule for all. Maybe you can write this as T dash for all. This is how you type for all statements. It's not about terms of for all statements. It's about actually ensuring that a for all statement is well formed. And then I guess the other rule, which I mentioned, is the typing rule for the actual construct type. So we also have a rule that in any context, type can be synthesized to type. So why are we doing this anyway? Well, I said that in the context in which we're working, we're going to have to mix terms and types. And as soon as we mix terms and types, we have problems where we're able to form meaningless expressions that definitely do not classify terms, because you can't quantify over a lambda expression. And so what is a type then? A type is anything which meaningfully can be said to classify terms. You can also form, if types are logical statements, false logical statements, in which case false logical statements will not have any terms, but the question of whether something is a term of that can still be posed. Whereas for things like this, they're non-starters. If we admit them into our system, we're going to have a lot of problems coming up. So at the very least, if we want to put anything at the right-hand side of a type checking statement, it should have type check to type. And then when it comes to for all statements, which are expressions, now that our types are expressions, each expression has a rule corresponding to it, right? When we were doing type checking and type synthesis, we might have had a different version of type checking and synthesis rules. For example, when we had and introduction, we had two versions of the rules, synthesis and checking. But if we look at the monodirectional rules in which we only have colons, then every single rule corresponds to a term construct, right? So the and intro construct corresponds to the and introduction rule. Similarly, or intro 0 corresponds to the or intro 0 rule, or I0 rule. And now that everything that we had as a type before is also going to be thrown into the world of our expressions, we also need to say how these constructs, which typing rules corresponds to them. And this is the typing rule for the for all construct. This is the typing rule for the type construct. Does that make sense? So this takes a lot of time to get used to. Now I'll say one more thing today. So to remind you, where were we going with this? So we start off with this, the BHK interpretation of a proof of for all x in T, W is what? Is
It's a function
yes, that does what?
that takes a proof and returns a proof.
Sorry, I didn't hear that.
That takes a proof.
Let's say a term
I'm sorry, a term.
of type T and returns what?
Proof of type W.
But is it W though? Or is there one more thing that we have to do? So let's say it takes a term, let's call the term T, little t. Then it returns a proof of what? Think about the example that we had at the very beginning of the lecture. We had this rule. if we have a proof, let's say f is a term of this type. In other words, f is a proof of the statement for all x and t w, right? So an example that we could have had is that the statement is for all natural numbers n equals n. Then if you take a natural number and you apply it to that proof term, we should get a specialized proof term that proves, for example, if a is z, that gives us a specialized proof for z equals z. So what are we actually returning? It's a proof of what?
As you said, it's a specialized proof.
Yes. So what does it actually prove? It doesn't prove w. It proves instead. So going back to the names that we had before.
Okay.
So we're saying that it's a function that takes a proof, that takes a term t. It takes a term t of type t, and it returns a proof of what?
W of type W.
With what?
It's like we substitute the big X with a little x.
With
In the
not little x. The
Little-
term is
and-
what? The term is,
little t.
yes. So in order to form the results, the type of the results, the result may in general involve x. For example, inequality types. Inequality types, they involve a term. And so in order to form the correct type, we actually have to substitute. If x occurs in W, and it is allowed to occur in W. Why is it allowed to occur in W? Well, look at the typing rule. For this to be a meaningful type, W has to be a type under the assumption that x has type t. So x is allowed to occur in W. If x did not occur in W, then we wouldn't have had to add x to our context. So we do have to substitute. So that's what suggests that since it's still a function, the proof term should be a lambda. And then because we've mixed terms and types, every single language construct corresponds to a rule, a unique monodirectional rule. So this corresponds to the for all introduction rule. This will correspond to the for all elimination rule. And then this is a special case of this. Actually, we can say, actually, we can make that. Anyway, the rule that corresponded to this was this typing for all rule, right? The rule which said when a well-formed statement, when a for all statement was a well-formed type. And then the rule that corresponded to this type construct was t-type. And the rule that corresponds to variables is still the variable rule. Now let's talk about what it means for the arrow to be a special case of for all. So before we said that if x does not occur in W, then we discussed substitution today. We spent a lot of time discussing substitution, right? If x doesn't even occur in W, then what happens when we substitute x for t? What do we just get?
Just W?
Yes. But then This is the same as a proof of T implies W, right? Because a proof of T implies W is a function that takes a proof of T and returns a proof of W, right? So what should happen is that T implies W is syntactic sugar for all, and then we should put a meaningless variable. Let's use an underscore to mean that the variable does not matter. This. Now, underscores are not allowed to occur in variables. Let's say that underscores underscores do not count as variables. So if underscore occurs in W, give an error. In which case, if we look at this rule that we had before for typing for all statements, so let's write that statement down below. So below, we had this idea that for all x in T, W, that expression in any context can be interpreted as a type provided what? What did we need to check?
First, that T is a type in the context gamma.
Yes.
Type checks to type, yeah.
And?
Then in the context of gamma, along with the fact that X is of type T, we have that W type checks to type.
Yep. So this is the typing rule for all statements. For implications, on the other hand, an implication is always changed to this statement, right? And if we have an implication, then we automatically translate it to underscore in T, W. So when should this type check to type? Sorry, when should this synthesize type? So underscore is not allowed to occur in W. Basically, we just don't add it to the context, right? So that's the same as saying, this is saying that T implies W is a type provided two hypotheses, provided that T is a type and W is a type, right?
Yeah.
So then this rule is slightly different because the context doesn't get changed. And let's call this rule the typing rule for implications. Although really, when we're just trying to type for all statements, we check whether the variable is an underscore. And if it's an underscore, we use this rule. We don't add underscores to the context. So in other words, since we have that typing rule, and that's somewhat distinct from the other rule, although you can think of one as a special case of the other, the typing rule for this construct is the T implication rule. So now if we look at this universe of expressions, then we have for every single expression provided a typing rule. And the typing rules are unique in the monodirectional setting. So in other words, type checking and synthesis are also syntax driven even when we've intermixed terms and types. So I'm not going to, we're not anywhere yet. We still need tomorrow's class before I can assign the homework for predicate logic. But until Wednesday, I've covered a lot of material, and this is very tricky and very subtle. So your homework is to review this lecture and also start reading Prabhakar's notes, although I'm departing a bit from Prabhakar's treatment for predicate logic. For example, he does not explicitly state these typing rules. He states that it's easier to give the code than the typing rules, which I disagree with because I think it's less clear. So I'm giving the rules explicitly. And I should really type something up about these. But I like this presentation where now that we've mixed terms and types, every single expression nonetheless has a unique monodirectional rule corresponding to it. So that syntax, type checking, and type synthesis are still syntax driven. Does that make sense? Oh, and then, right. Oh, sorry. I need to also tell you what these rules are. What are the introduction elimination rules for implications? Before they were rules for implications. Now they're rules for all. So, well, okay. If you have a lambda, how do you type a lambda? So lambdas, you can only type check lambdas. You can't type synthesize lambdas. So this should type check to T implies W, provided what? What did we have before for lambdas? Oh, I mean, okay, let's say we have the expression, okay, sorry, I don't want to, I shouldn't write arrow here. Right now, I should write for all. Because we rewrite arrows as for alls. So this should type check to for all, let's say, let's keep the variable the same. So terms are equivalents to alpha equivalents, and I make my alpha equivalent terms be so that these two variables coincide. Before in propositional logic, we had, for example, lambda xx type check to A implies A, right? What did we check when doing that?
That in the context that X is of type A, we have that X is of type A.
So we took our context and we added to it that little x had type T, right? Now, notice that here, there's a binder, right? There is a binder here, and there is a binder here. Yes?
Yes.
Now, I've made both of these coincide. So using alpha equivalence, I make these two coincide. I make the variables coincide. And now I need to take T, and this should type check, right, to W, where W, now occurrences of X and W are also meaningful. Yes?
Yeah.
Okay, but here's the thing. I've just added X is bound to T to my context, right?
Yes.
But this expression right here might not be a meaningful type. For example, it could be that T is lambda x dot x. Then that would be an issue, right?
Right.
So I have not yet checked that this is a type. But instead of checking that it's all a type, let's just check that the thing that I'm adding to my context as a type binding is a type. Because if what I'm adding to my context isn't that binding, then we're going to get very bad program behavior. So let's also check, at least partially, that T type checks to type before adding it to the context. Then W, if W isn't a type, that'll get caught in the next step, because this might not have, if this wasn't a type, then if T is a type, then it's W that's not a type. And then that'll get caught in the next step. But this at least checks that this expression, at least the T part is a type. At least that part is well formed. So our, and then this rule, it's, so instead of implication, it's for all, and this is the for all introduction rule. So this is our new version of the for all introduction rule. And then the for all elimination rule was the first rule that I wrote in lecture. Let's think about that. So suppose we're looking at a statement and we're looking at an application, right? So I'm going to say that that synthesizes type W. Or no, let's not write what it synthesizes. So what do I do when I'm trying to synthesize the type of an application? What's the first thing that I have to do? Well,
Whether F synthesizes to some kind of implication.
yes, except now we don't have implications. Now our implications are a special case of for alls, right?
Yes.
So F should synthesize to some for all type. Let's say for all X in T W. Okay, so we're going to return that, assume that everything returned by type synthesis is a type. So this is definitely something that's a type, if it's returned by type synthesis. That should be an invariant. Now what do we do? Now we need to do what?
I mean, basically.
Type check T.
Right. A. But what are we going to type check A against?
Big T.
Oh, yes. T. Oh, right. And yeah, actually, that's good. B, we don't have to add X to our context. Contexts don't change. They never change. Yeah, sorry. Let me erase that. Type checking A to T. A should not involve X, of course. It's completely separate. That's F, that's A. A is a separate term from A. So we just type check this to T. And T makes sense on its own. X can't be involved in T. Okay, so after that happens, what type do we synthesize?
Proof of W?
Is it just W?
No, it's we have to do substitution.
X.
That is X replaced with A. Little A.
And so this is the for all elimination rule. So these rules are like the introduction and elimination rules that we had for implications, except implications are now a special case of for all. And with for all, this is what the rules become. So this is the for all elimination rule. This is the for all introduction rule. And then for variables, well, the variable rule is as it was before. Before adding anything to a context, we ensure that it type checks to type. So everything in our context is going to be a type. In which case, in the variable rule, if we just have a context gamma, and then we take some variable, then it's going to type synthesize based on, let's say, type synthesizes to T, given that X colon T is in gamma, right? In the context gamma. So this is the variable rule as before. That's the language construct corresponding to variables. So here, let's look at the lambda calculus constructs. This is the rule that corresponds to lambdas. This is the rule that corresponds to applications. This is the rule that corresponds to variables. But we've also added types into our language as expressions. So this is the rule that corresponds to for all types. Then arrow types are a special case of for all types. You should sort of consider either one of these rules to be the case. Basically, if there's an underscore, then we don't add it to our context. And finally, there's the rule that's just type. Type synthesizes type. And this is an axiom, so it doesn't have premises. And then I can call this T-type. So now that we've mixed terms and types, everything that was a type before has to have a corresponding typing rule, because now types type. Types should type to type. Which is why for all of these three rules, the conclusion is that we're able to synthesize type. But types have to be well formed. For example, if you have an implication, then the left-hand side and the right-hand side have to be well-formed types. And if you have a for all, the thing that you're quantifying over better be a well-formed type, and the results should be a well-formed type. But the result might involve X, so that's why we have to add it. And that's why this case is more general than the implication case. But then for the terms before, we had them here, except now they're not for all statements. They're universal quantifications. And then for the results type, if W involves X, we need to substitute. And for this case, if we're type checking and this is provided by the type checking. Before adding it to the context, we check at the least that it's a well-formed type. Otherwise, we'll be allowed to type check terms that are not, to things that are not types, and we do not want that to be the case. So here are the 6 rules corresponding to this new starter grammar in which we now have 6 different variants for expressions and no notion of types on their own. Okay, so that's more than enough material for today. Remember how we did substitution, how substitution was tricky? Yes, well, so we did this and we also changed the grammar to have now these 6 variants. Any questions? This was a very, 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 very packed lecture. We covered a lot today. Your homework is to go through this again. No questions? Okay, have a nice day. I'll see you on Wednesday. This week is the hardest week of materials, so if you keep up, you're doing a very good job. This is very tricky stuff. This week is the most intense of all of them. And it's really, I found this tricky even. I found this tricky for months, I think. But I had to reword it so that it fit my understanding. But my understanding might differ from your understanding. So anyway, definitely you need to think through this. Okay, have a nice day.
You too.
Bye.
Thank you.